fast. Who's one of our PhD students. Take it away, Julen.
Yeah, can you hear? Yeah, all right. Okay, yeah, so I'm going to present a project that we have been working on for several times with a pretty large number of co-authors, as you can see. And the main idea is to understand how climate affects forest demography at the tree level. So here you can see like the distribution of forests worldwide, as we have seen all along the meeting, right? And well, it's pretty clear that all these forests are affected by climate change to some extent. And there have been documented like several drivers of affecting forest dynamics. For example, like here, as you can see, like CO2, temperature, drought, etc. But on the present work, we are going to focus on these two, more or less, like temperature and aridity or drought. And here, well, let's take a look at the data first. So this is the tree mortality data, as we have seen, like, for example, yesterday, Susan's presentation and so on. And here, well, here we can see changes in tree density. The first thing that we see is that it's very difficult to see anything, right? Like we can see like green dots, brown dots, and so on. So we are working with a lot of plots, a lot of species. In this case, we are working with 74 species, but it's hard to get any conclusions from these pictures. So this one, it makes a little bit clearer idea. So here you can see this kind of density and interval plots, where we can see, for example, how South Europe, or in this case, Spain, it's increasing in tree density, but Western US, it's decreasing, for example. But here, the issue is like, okay, yeah, we know what's going on in terms of density, but one of the biggest questions that we are addressing here, it's like, how will tree species respond to changing climatic conditions? Okay, so we know what's going on at the plot level, but what's going on at the species level? And when we try to answer this question, and we go to the literature, we can see that a word is very often repeated. That is this one, well, a synonym, a divergence, or disparity, or multiple directions. So clearly, we don't know what's going on. So at this point, we try to better understand or try to answer this question. And here, well, yeah, so we know that climate affects tree demography, right? And here, what you can see this kind of joint division plot. And for example, here in the x-axis, we have this mean temperature of coldest quarter. And on the y-axis, we have all the species abundance that we are working on, but these are just the European species that we're working on with. This is just an example. Okay, so we don't have a very large temporal scale, but we have a very large spatial scale. So we try to work with this spatial extent to answer our question about how climate is affecting tree demography. So another variable apart from climate, it was that, okay, there are forests that we were talking before about old growth forest or young forest, right? And clearly they are not going to answer in the same way if it is a young forest or if it is an old growth forest. These pictures are from my hometown in the Basque Country, in north of Spain. It's Fagus Silvatica, or beach. And for example, the left one is a young forest and the right one is an old growth forest. So there might be some kind of interaction between climate and forest development. So we try to consider this variable too. So our objective was to better understand how tree species niche position or climatic affiliation, in this case, determines demographic responses to climate for young and mature forests. So how was our approach, right? So this is, for example, a beach distribution along Europe, and here we crop it with minimum temperature. So you can see like how minimum temperature is distributed along beach range, right? So from that one, we can get this one, this plot. So in this plot, we have in the x-axis, we have this minimum temperature. And on the y-axis, we have the abundance. And the pretty cool thing here is that, I don't know if you can see this dashed line. This dashed line, it means the median climatic value obtained from this map. So the median, it will be somewhere there. I don't know. Yeah. So the question is, when you are getting farther away from this median position, how abundance change, for example? And well, here we have two species. Like I added another species just to show you as an example that we might have a Fagus sylvatica that it is cold affiliated, and holm oak that it might be warm affiliated, right? So, well, I like putting faces to people and also to trees. So here on the left we have beech forest, and on the right we have holm oak forest. Yes, so we know what we are working with. So the next plot, we have this dashed line. We transform to as absolute units. So now the dashed line is on the left. So now what we can see is, okay, when you are farther away from this dashed line, how the abundance decreases. Okay, in absolute terms. So these plots are the same, but just in this one is in absolute terms. But we weren't interested in abundance. We are interested in demography, right? So with this one, we created our hypothesis. So when talking about demography, so abundance is in one time step, in one time interval, but if you have two time intervals, you can see changes in abundance, for example, right? And this is demography in the end. So on the y-axis, we have changes in abundance, right? Changes in density in this case. And on the x-axis, we have this distance to the niche position. And our hypothesis, it was that, okay, so maybe those species that are warm affiliated, they will have other responses than those species that are cold affiliated. So this was our hypothesis at this point. So let's see if this works. But we have the other problem about young and mature forest, and after a very long discussion about what is a mature forest and how to characterize mature forests, for example, here we made clusters of maximum regional productivity. So productivity, after these long discussions, we thought that productivity is based on mean temperature, precipitation, and nitrogen availability. So here in this colorful map, let's focus on that part. So in North Finland, right? And you can see more or less that they have the same color. Okay, so this is a cluster where nitrogen, precipitation, and temperature, it's very similar in all these places. So these are two plots from this, I don't know how many there are, like let's say 50, and I started two plots. So you might have a maximum basal area of this cluster. So it is how this plot, what's the maximum that can reach this plot. So it will be the blue one, the blue dot, and the red one, it will be, where is this plot? Where is the basal area of this plot? So if you divide one by the other, we obtain that the plot that it's here, it's a young forest because it's farther away from its maximum, whereas this one, it's closer, so let's say that it's mature. So we obtain a value between 0 and 1, ranging between young and mature forests. Okay, so now we have all our variables, we have distance, we have mature and young forest, and then we made a lot of models. So we fit a lot of models, like one model per species for the 74 species, and in each model, so this then, well, we did all model diagnostics, a lot of sensitivity analysis and all this stuff, right? And when we trusted our models, these are the predictions of the models, okay? So in these predictions, the predictions of changes in tree density, so our response variable is tree density, okay? And what happens if you increase 1 degree in temperature and if you increase 0.1 in aridity index? So if you are farther away, 1 degree from where you are, from this population it is, what happens in terms of density, right? So this is the gray one, it's the predictions without changing anything. So this will be like kind of the real data. And then the young forest, so there we set the forest development value to very low values. So let's assume all these forests are young. So what will happen? And let's assume now that all these forests are mature, that what will happen in terms of tree density. And now I added a third species here because, well, I thought that, well, these are increasing, but this one is decreasing. It's a species from southeastern US in this case, but we did this with all the species that we have in our, with these 74 species, right? And well, then we have, let's focus on mature forest, on the yellow one, okay? And let's remember our hypothesis. So our hypothesis was that the niche position will determine how this changes in tree density. Okay, so let's say that warm affiliated species will decrease less than cold affiliated species. But we did this also with aridity. But for the example, I will just tell you what happens with temperature. Okay, so here, to answer our hypothesis, here it is like in these predictions, we just increase 1 degree in temperature from current stand conditions for all the plots containing one of these species. Okay, and these are just for mature forest. So here, this is the prediction for the beech and the other 2 species we have here. And on the x-axis, we have this niche position. Okay, so these ones are warm affiliated and this is a cold affiliated. So we expected to find this kind of patterns. Let's say maybe these species that are warm affiliated are doing better than the ones that are cold affiliated. But what we have observed so far, well, yes, before that, let's focus just on the median point because, well, this is the uncertainty, okay? But since we have a lot of species, I think it's easier to just focus on the median point, just for the sake of clarity. And this is what happens, okay? So we don't get any clear pattern. So this is, well, these are GAN models that we fit. These are the median points for all the species, for all the predictions that I showed you before, not just the 3 ones, but all of them. So we somehow might expect this kind of patterns of this one, and that would be super cool, but this is not so easy. And then we have like for gymnosperms, angiosperms, and the black line is for all the species together. But this is just for temperature, but we did it also for aridity, for young forest, and not just for this number of stems, but also for basal area. So now what I would like to check is, okay, here we don't observe any pattern, but let's see if we try with functional traits, for example. Maybe this axis will respond to a functional trait. I don't know. So we are in this step, and if you have any ideas, so we can have a chat later. But so far, the multiple directions, it seems pretty obvious. So as concluding remarks, I would say that I copied Adriani, species matter. Like if we want to predict how the world's forest will respond to climate change, we need to know how different species will respond. But so far, what our results suggest is that there are large divergences. So some species are responding in one way and others in the other one. But the question remains open. Is this divergence due to really multiple directions, or are we missing something that is behind that we haven't seen yet? So this is like an open question, and we are working on trying to answer this question now. So thanks for your attention. And I will particularly thank these guys that have helped me a lot. And yeah, thanks if you have any question.
Questions for Julen? Yeah.
Thank you very much. I was wondering, does your analysis make the assumption that a species is best suited and grows best where it's also most abundant? Mm-hmm. And is that a reasonable assumption?
Yeah, no, we are not assuming that because, well, previously we assumed that. Previously we assumed that in our data set, where is the highest abundance, and we made it like a weighted mean, let's say a weighted mean of temperature mean and abundance. But the problem with our data set is that we didn't cover the whole species range, so we switch it. So we download the whole species ranges, and we select the median, let's say the temperature minimum, the median value, considering the whole range. So we are not talking about abundance there. It's like the median value of the whole range. Now it's like that. Yeah.
Other questions? Yeah, Martin.
So I have a general question. So based on your data set on different tree species that you tested, what the trees of future would look like? What kind of species we could use in terms of the species diversity?
I didn't get the question very well, sorry. Can you?
So what are the trees of future? So what kind of species?
Yeah, I don't know, actually. I would like to know it, but I don't know yet. I don't know. Like what I would like to, like that would be great, but maybe not. It would be like just to add some clarity to this question. So with that, we will be able to somehow predict what will happen. But at this point, I think with the results that we obtain, it's very hard to make any predictions because it looks like everything is going on like randomly, you know, but maybe it's like because we are missing something. But yeah, I don't know.
I saw Carolina has a question, but I think we're going to move on just to keep to time because I know people have to catch flights and trains and things. So thank you, Julen. It's not going into presenter mode for some reason. So I'm not getting the two screens.
Last time we didn't close the presentation, it was. Yeah, no, everything is. No, look, it's open here.
So, oops.
No, it's not this one.
It's
Perhaps this.
Guys,
so
there we go. Why it's not giving the options.